Hello everybody. In this lecture I'm gonna go through last part of the chemical kinetics, and we will be discussing activation energy and also the relationship between activation energy and temperature. What will happen if we increase temperature of one reaction, and how about the rate constant? And after that one we will switch to mechanism. I will show you, what's the meaning of the mechanism, and what's the name of each step, how to get the, the rate law for each step. And at the end, I will end the lecture with catalyst, and I will, show you two graphs, and you will see the effect of the effect of catalyst in one specific reaction. Okay, so we go with this. Let's assume we have this graph. Okay, we have a reaction, and the reaction can be anything. I have reactant, and I'm transferring them to product. Okay, so let's say I have carbon dioxide, and I want to turn carbon dioxide to carbon plus oxygen. So this side we have reactant, and that one product. Okay. Gap between reactant and the maximum point is the energy that you have to give the reaction to initiate at least one cycle. And we call this gap, we call it activation energy. We show it by here. EA, we say activation energy. And the maximum point, we call it TS, or T dot S, T dot S dot, or transition state. So what we do in reality, we give energy. So I'm gonna say add energy to reactant. So I'm adding energy to the reactant, and this energy is equal to the activation energy. I'm gonna try to lose some bonds or rearrange some bond angles in a way that I can move to the product. So for example, in this case, I have carbon dioxide. I want to break these two bonds. I want to break them. I need to have energy to break those two bonds. So we have to give it energy. And then you will get two oxygen will see each other, and they will generate O2. And you will see later on that if you change temperature of a reaction, activation energy, it can go up or down. It depends whether you're talking about exothermic or endothermic reaction. But for sure, activation energy is subject to temperature. Okay, activation energy is subject to temperature, and I'm going to discuss that one. Okay, so here is a formula. We have K, rate constant, is equal to A multiply E, the power of EA over RT. K is rate constant. A, you can call it frequency factor, and R, gas constant, and number for it is 8.314 joule over mole to Kelvin. Temperature, T is the temperature, in Kelvin unit. So it's a temperature in Kelvin unit. And what else? EA. Okay. Here, please look to the unit of R. R comes with joule over mole to Kelvin. Because R, it comes with joule, EA must be in joule unit. Be careful about this one, please. E must be in joule unit. Okay, so it will have joule. If they give you kilojoule, you have to transfer it to joule. And EA is the activation energy. Okay. This one, it says K equal to A multiply E to the power of minus EA over RT. Okay, handling this one, it kind of like a bit hard because it's exponential. And I'm going to try to make it, linear equation, so then it will be easier to track it. But let's go through all the factors that we have. K is the rate constant. It's going to tell you how fast the reaction is moving. A is says a frequency factor. What does it mean? You can call it number of good collisions. Okay, number of good collisions. How many good collisions we have? And I will talk about good collisions. A good collision is the collision that has enough energy to pass the barrier. A good collision is the one that has enough energy to pass this barrier, and also it must be in the right direction. Like if you have a collision between two, atoms, they must be the product, not like, you broke, for example, you broke this, you broke, like the bond between, carbon and oxygen, and then now you have, let's say, you have carbon plus one oxygen and another oxygen. If you, like let the oxygen to collide with the carbon, you'll get, CO. That's not the product I'm looking for it. I want to have collision between O and O to get O2. So as you see, like not any collision is a good collision. So what I'm going to do, I'm going to get natural log from both sides of this equation, and it will give me ln of K equal to ln of A multiply e to the power of minus EA over RT. Okay. Reminder, ln of X to Y, we can write it as ln of X plus ln of Y, and ln of E to the power of X, you can write it as X ln of E, and ln of E is equal to 1, so that's going to give you just X. Okay, so from this formula number 1, I get ln of K equal to ln of A plus ln of e to the power of minus EA over RT. So we call it 2. Ln of K equal to ln of A minus EA over RT ln of E. And this is equal to 1. So we get ln of K equal to ln of A minus EA over RT. I'm going to call it 4. I will rearrange the formula and I will get factor from 1 over T. So I'm going to rearrange the formula as ln of K equal to minus EA over R multiply 1 divided by T. So it's going to be RT plus ln of A, and I'm gonna call this one 5. Okay, so let's take the 5 and rewrite it. So 5 is ln of K equal to minus EA over R 1 over T plus ln of A. I'm going to say y equal to mx plus b. Now let's define y, m, x, and b. Y is equal to ln of k. So k is going to be equal to e to the power of y. So if I have y, I can get k. M is equal to minus e over r. So the activation energy, we can calculate it through slope minus slope multiply r. Okay, if we know the slope, we will multiply it by r. We will get the activation energy. And b, the intercept, is equal to ln of a. So the frequency factor, it will be equal to, again, e to the power of b. So I'm going to use this 1, 2, 3, 1, 2, 3 to calculate, activation energy, barrier, and frequency factor. So we have one example in your slide that I'm going to go through it. Okay. Here's a question. It says we have a linear equation. Look to this one. It says ln of k versus 1 over t. I'm going to bring it down here. It says, sorry about this one, put it that way. Okay, so we have ln of k versus 1 over t, which is the variable. So slope, this is going to be the slope. And this one, it will be the b, or the intercept. Okay, so now it says find the activation energy and find the frequency factor. We can also calculate, the activation energy and the rate constant if we get, specific temperature. Okay, so let's go after it, and I go with here. So I do have the linear equation. Slope is going to be equal to slope. It will be equal to minus e over r. So activation energy is going to be minus slope multiply r. Slope is minus 1.12 multiply 10 to the power of 4. What's the unit for it? Check this one. 1 over t, it has unit of 1 over Kelvin. This one has no unit. No unit. So if you want to add it to hold this term, m multiply x, hold this term must be without unit. We know x, which is the variable, is 1 over Kelvin. So anything that we are multiplying, it has to be in Kelvin, because then Kelvin by Kelvin will be cancelled, and I will not have any unit here. Okay, so this one is going to be Kelvin multiply r. It will be 8.314 joule over mole to Kelvin. Now you cross Kelvin by Kelvin, and that one is going to give you joule over mole, which is the right unit for activation energy. And I forgot to add one negative here. There's a negative here from the formula, and that negative comes from m. So we have 1.12 for 4 multiply 8.314. I got it. 9.31 multiply 10 to the power of 4. So double check it. 1.12 1/4 multiply 8.314. Yes, it's the same number. So activation energy is equal to 9.31 multiply 10 to the power of 1, 2, 3, 4 unit joule over mole. So we got the activation energy. Okay, we got the activation energy. How about B, which is ln of A? And we can calculate this one. So I go with here. I have B, which is the intercept, is equal to 26.8. B is equal to ln of A. So ln of A is equal to 26.8. That means A, it will be e to the power of 26.8. And that one is going to give us the frequency factor, or number of good collision. 26.8. 26.8. Okay, 4.36 multiply 10 to the power of 11, double check. We have 26.8. So the number is 4.36 multiply 10 to the power of 11. Okay. So last thing that I'm going to add to this equation, okay, they asked me find the activation energy and find the frequency factor. I got both of them. I got the A and I got you the activation energy. Last thing I'm going to add, to the question, I'm adding find K if the temperature is equal to 298 Kelvin. Okay. So we go Y is equal to minus 1.12 multiplied 10 to the power of 4 here, X, and we go plus 26.8. Okay. And I have ln of K equal to minus EA over R 1 over T plus ln of A. So the only thing I need to do, technically, just put the temperature and get, get the ln of K. If I have ln of K, I can calculate the K. So you can use any of this. Okay, you can use any of this to calculate, the K. Okay, so I go here. I go with the second. Ln of K equal to activation energy. We got it minus 9.31 multiplied 10 to the power of 4 joule over mole divided by R, which is 8.314 joule over mole to Kelvin, multiply 1 over T. T is 298 Kelvin, plus ln of A. Ln of A is equal to this number. So you can say ln of A, which is 4.36 multiplied 10 to the power of 11, and it's going to give you the answer 26.8. So simply I say 26.8. Check this. Joule by joule, it will be cancelled. Mole by mole, it will be cancelled. And Kelvin by Kelvin. So we got nothing left as a unit, and now I can add it to the 26.8. Okay. So we have the activation energy. Just want to be careful. Okay, so I have minus 9.31 power of 4 divided by 8.314. Okay, and if you divide this new number, you will get this one. Okay, so I could easily replace x by 1 over t, which is going to be 1 over 298, and it will give me the y, and then y is equal to ln of k. So then I can calculate the k. Okay, so this one, if you do the calculation for it, it will be equal to this number. Okay, on purpose I use this one to show you that like it doesn't matter which one you use. Okay, so I go with here. I have ln of k equal to minus 1.12 multiplied 10 to the power of 4, and we have 1 divided by 298 also, so let's say multiply, plus 26.8. so ln of k divided by 298, answer is here minus 37.58 plus 26.8 minus 26.8, it will be minus 10.8. so k it will be e to the power of minus 10.8. Got it. 2.04 multiplied 10 to the power of minus 5. Okay, so let's double check it. And I go with minus 10.8. Okay, it will be 2.04 multiplied 10 to the power of minus 5. Okay, that's the K rate constant. Okay, so whether you are using this or this one, answer is going to be the same. If you use this one, be careful. The x is equal to 1 over t. So you put 1 over the 298, you get the y. Y is equal to ln of k. So if you have ln of k, you have ln of k. Now you say k is equal to e to the power of that number. Okay. Or you go with this one, ln of k equal to minus ea over r, 1 over t plus ln of a. Okay, so we did an example about using this equation, or like a correlation between or connection between rate constant and activation energy and temperature as well. Okay, so I said in order to run a reaction, we need to have good enough energy to have good number of collisions, and not any collision is a good collision. Collision must come with good number of energy and right direction. Okay, let's look to this one. We have a reaction that it says NaCl plus NaCl, and we want to get 2Na plus Cl2. So here have oxygen let's say in this case actually, or central atom, it can be like if it's oxygen, so I go with here chlorine. Let's say this one is nitrogen. Then I add, okay, this one cannot be actually, sorry, but this one cannot be, it has to be nitrogen. So say you have oxygen, you have chlorine, then you go nitrogen, oxygen, chlorine. Okay. Look to this. What you need to do, you need to generate, Cl2. So you need to have a collision between two chloride. And if I say O, nitrogen, chloride, and I put oxygen in front of it, oxygen, let's say, it will kick for example, the chloride. If they go head to head, product is not gonna be Cl2. It is gonna be ClO. If I put, let's say, I don't know, with nitrogen in front of it, nitrogen also is not gonna give me, a good one. But if I put chloride and say nitrogen, O, this time, if I do interaction between these two, I will get Cl2. Okay, I get Cl2. And if you break that one, it will give you NO. And if you break that one also, you will get another NO. So 1 NO plus 1 NO, we got 2 NO. And collision between two chlorides gave us Cl2. So as you see, you need to have good collisions, a collision that comes with enough energy, or I have to say high energy, high enough. And the second thing is the right direction. So these two, they had enough energy. Product, it can be, let's say, it can be one, it will be NCl, the second NO, and we might get ClO. Okay, might get all this in three products. Okay. Only one of them gave us actually the right product. The rest are side products. So they gave us some of the product, but not all of them. So that's the reason I said this is not good. It's not in the right direction. It's not a good reaction. But in this case, if I let the chloride to hit the second chloride, I will get a bond between them, will give me Cl2. We will lose the bond between the chloride and nitrogen. We're going to release NO from one side and another NO from the second side. So you have to give it enough energy. That means you need to play with the temperature, and it has to be right direction. Okay, so that means you need to have a really high number of collisions to be sure that you're gonna get, collisions with high energy and in the right directions. Okay, and that one, we show it by activation, by frequency factor. Okay, look to this graph. Okay, so we said the activation energy is subject to the temperature. If you have enough, like if you have enough energy, or if that molecule or atom, it has enough energy, it can move faster. And because it's moving faster, that means it will collide, or it will have collision with other, atoms or molecules. And so there is a chance to get the product. Let's check these two. The graph that on the left side here. It says collision energy, and this one a fraction of collisions. Okay. When the temperature is low, okay, energy of that collision is going to be low. Okay, so this is E1. But you will have higher number of, collisions with that energy. It's like, if you are driving with 50, 60 miles, there is less chance that to have a car accident. You are in control of your car. But if you are driving with 110 mile, that's gonna be, hard. And there is a chance that you will have collision with something, or maybe you will be arrested. God knows. I hope not. Okay, but check this one. When we increase the temperature, T2, the peak or the graph got stretched. Okay, got stretched. And now we will have, if you check this area, we will have bigger area that's passing the minimum energy that we need to apply to ignite the reaction. Okay, this is the activation energy. When it was T1, this area was with enough energy in right direction. Okay, or at least just say energy. But when we increase temperature, now entire this area is capable of doing the reaction. Okay, so as you see, by increasing the temperature, we make the reaction more possible to be happen. Okay, and again, as you increase the temperature, activation energy is going. As you increase the temperature, energy is going up. Energy of the molecules. That means you do have enough energy to overcome the activation energy. And check here, fraction of molecules versus energy. As we increase the temperature, number of molecules that they have enough energy to pass the activation energy got higher. Hold this one. So I'm going to say possibility of running in reaction is subject to the temperature. That's the reason we say active K equal to E, number of collision, multiply EA over RT. If you divide it by temperature, that means, temperature, it will make the activation energy smaller. Okay, the gap between them, between reactant and transition state, it will be smaller. Okay, or you will have enough energy to overcome that one. Okay, so formula that I practiced for you was ln of K equal to minus EA over R multiply 1 over T plus ln of A. In this case, we have temperature at this T. Let's call it T1 for now. And if I change it, because I changed the temperature, K, it will be a different number. K is subject to temperature. So this one, it will be 1. Now we get minus EA over R 1 over T2 plus ln of A. We are dealing with T2. Okay, so K is constant if T stay constant. Okay, if T stay constant. So K directly subject to the temperature. I changed the temperature, so K is going to be a different number. Okay, let's subtract them. Let's subtract the first moment from the second. Okay, so we're going to get ln of K2 minus ln of K1. And then we get minus EA over R multiply 1 over T2 plus ln of A for the second formula minus EA over R 1 over T1 plus ln of A. Okay, let me close it. Okay, so here we have ln of x minus ln of y. We can rewrite it as ln of K2 divided by K1. So I get ln of K2 over K1. And I'm going to get factor from minus EA over R. From first one, I will have only 1 over T2. What's happened with the ln of A? This ln of A, it will be cancelled by that ln of A because it says minus ln of A. So from first one, I will have only 1 over T2, and then I said minus. We got factor from minus EA over R. And then we will have 1 over T1. Okay, and this is the second formula that you will use. Okay. So the first formula, it says ln of K equal to minus EA over R, 1 over T plus ln of A, only 1 temp. Okay, we have only one temperature. The second formula, it will be ln of K2 over K1 minus EA over R, 1 over T2 minus 1 over T1. Okay, we have two temperatures. Because we have two temperatures, we're going to have two Ks, two rate constant. So we should be able to calculate activation energy of any reaction, any specific reaction, by, like having two temperature and two rate constant. And I'm going to practice one question about it. Here's the question. It says, if activation energy of one specific reaction is 108 kilojoule over mole, and they give us a rate constant in this temperature, they're asking what's the rate constant when temperature goes to 366. So we have the activation energy, we have R, T2 we have it, T1 is given, K1 is given, K2 we are looking for it. So let's go with, here. We're going to use the second formula. So we want to use this. We have K1 is equal to 4.60 multiply 10 to the power of minus 6. And is 1 over S. Temperature says 1.85. You transfer it to Kelvin. K2, we are looking for it. T2 is at 366. And activation energy, it says 108 kilojoule per mole. We want it to be in joule. Remember, because R is going to be in joule. R is 8.314 and is joule over mole to Kelvin. So we have to get the activation energy in joule. Multiply this one by 1,000. So it will be 108 multiplied by 1,000. And it will be joule over mole. And this one, it will be 275.00 and unit Kelvin. Okay, so I have all except K2, so I should be able to calculate K2 through this formula. Okay, so I go with ln of K2 divided by K1, and it's going to be minus EA, activation energy 108, multiply 1000, unit joule over mole, divide by R, which is 8.314, multiply, sorry, 8.314, and unit for it is going to be joule over mole to Kelvin, multiply T2 is 1 over, we said 366, minus T1 is 275. Okay, so get ln of K2 over K1. Let's get the answer for it. So I have, okay, 1 divided by 366 minus 1 divided by 275. Okay, negative number, multiply 108, multiply 1000, divide by 8.314. I got it, minus 11.7. Let's double check it. 108, multiply 1000, multiply, divide by 8.314. Okay, multiply 1 divided by 366 minus 1 divided by 275. So again, 11.74. Okay. So I got this one negative to negative, it will be positive, so it's 11.74 or 7. Okay, so now we can calculate, calculate the K2. So I'm going to say K2 over K1, it will be E to the power of 11.7. Okay, this one is equal to 1.26 multiplied 10 to the power of 45. Okay, cool. So now we can calculate K2. So K2 over K1 is equal to 1.26 multiplied 10 to the power of 5. So K2 is going to be K1 multiply 1.26 multiply 10 to the power of 5th. Okay, K2. K1 is given, and K1 was 4.660 multiply 10 to the power of minus 6, unit 1 over second, multiply 1.26 multiply 10 to the power of 5th. So this one I go with here. Multiply 4.6 to the power of minus 6. The answer is 0.58. So I got this one 0.5. Okay, if I go 3 sig fig here, 3 sig fig, unit 1 over second. So K2 is equal to 5.80 multiplied 10 to the power of minus 1, and it's 1 over second, versus K1, which is 4.60 multiplied 10 to the power of minus 6, and is 1 over second. So we increase the temperature, the rate constant, went up. Temperature here is 275 and T2 was 366 Kelvin. So as you see, by increasing temperature, rate constant went up. Okay, so now I showed you the correlation between rate constant and activation energy, rate constant and different temperature. And we did it for 1 or 2 temperatures. And now I will switch to mechanism and I will start that. And after mechanism, I will end the lecture with catalyst. Okay, what's a mechanism? Mechanism is the way that reaction moves from reactant to product. Okay, it can be one step or multi-steps. Okay, so the mechanism is the way that we transfer reactant to product. Again, it can be single step or multi-steps. Okay, and the one that is the lowest in rate, it will be the rate determining. So the slowest step, we call it the rate determining. A rate of reaction, it will be subject to rate of the slowest step. So technically, when you are measuring a rate of one reaction, you are measuring a rate of the slowest step. This one is gonna slow the reaction, and we're gonna read this one because the first one, it will be so fast that you don't see it, and you see this. Okay. Now, we have this reaction. We have 2 mole. We have 2 mole from NO plus O2. We get 2NO2. Okay. This is the overall reaction. So this reaction is going through 2 steps. First step, it says NO plus O2. We get, this is equilibrium because it's double errors. You have 2 reactions. One is moving to the product side and is generating NO3. And the second one is taking NO3 and it's breaking it to O2 plus NO. This one says fast. Okay. Rate law for this step. Rate law for this step. If you know steps of any reaction, okay, if you know the step, the elementary steps, we call this one elementary step. Okay. If you know them, then you say here, you say rate for this reaction is gonna be equal to K multiply NO. I see only 1, and then I see O2 only 1. Okay, I'm reading this one and that one through the coefficients. That's a nice thing with the elementary steps. If somebody gave you enough info and it broke the reaction, the overall reaction, to steps of the mechanism, then you can determine the rate law for each step. Rate law of the reverse reaction. Reverse reaction, we show it by, because it's still is the first reaction, we show it by -1. So we say -1 is going to be equal to K -1 multiply NO3, just 1. So I know rate law for each step just by reading the reaction. Okay. Next thing is NO3. We don't have it either inside the reactant side or the product. we are generating NO3 and we will use it later on. Because we don't have it either on the reactant or a product side, we call it intermediate. Okay. NO3 is an intermediate compound. Next thing, second step, it says NO3 plus NO, we get 2 mole NO2. This is slow. Okay. Because this is slow, it will be the rate determining step. Step that's going to slow entire reaction. So the rate law for the overall reaction, it will be subject to this. Rate law it will be here. Let's call this one K2 multiply NO3 just 1 and NO again just 1. Okay. Check this. We said because this is the slowest step, it will determine the rate law of the overall reaction. But see what we have. We have NO. NO is a reactant, but NO3 is intermediate. So how do we want to discuss rate of the overall reaction when we have concentration of reactant? I don't know how much, the intermediate. I don't know how much intermediate I have inside the solution. Okay. So that's the reason whenever we get intermediate inside the rate law, we try to transfer it to concentration of reactants. And I'm not gonna go through this one, is way higher than this, scope until now. Okay, until now. And I wish we had the like the equilibrium way before, so then I could discuss this one, because right now we have equilibrium, and I know many of my students don't have any idea about the meaning of equilibrium. Okay. Next thing that I'm gonna go through it is the molecularity. What's the meaning of molecularity? Okay. So we have the main reaction. It says 2NO plus O2, we get 2NO2. Okay. We have two steps. NO plus O2, we get NO3. NO3 is the intermediate. Rate law for this reaction, it says KNO multiply NO2. This is a rate for forward reaction, technically, if you call it. And that's going to be the reverse one. So if I go 1 here. Okay. And what's the meaning of molecularity? Molecularity, when it comes to mechanism, means number of particles that they are involved in each reaction. Number of particles. One particle, and I see here another particle, so the molecularity is equal to. Okay. Or look to this. You have one NO and one O2. So 1 plus 1, it will be 2. And how about this? Molecularity, we see 1 NO3 and 1 NO, so 2 particles are involved. Molecularity, it will be equal to 2. So molecularity means number of particles involved inside the reaction. Okay. If you know the rate law for each step, just look the coefficient, exponent. Okay. Exponent, it says 1, this one is 1, so that means molecularity is going to be 1 plus 1, it will be 2. It says NO2 plus CO, we get NO plus CO2. Okay, I have two steps. One says NO2 plus another NO2, we get NO3 and NO. It says slow. Because it's slow, is the rate determining step. Okay. because it's a rate determining step, so write the rate law for it. Rate law for this step, you go with here. Rate law for this step number 1, it will be K multiply NO multiply another NO. So it will be KNO2. Okay, it will be KNO2. So the rate law for the overall reaction, it will be K multiply NO to the second. So K NO to the second. Okay. If you know the elementary steps and you know which one it says slow, you got the rate law for the reaction. So the rate law for this reaction is going to be K NO. Okay, and sorry, this is NO2. Okay, and second step is fast, so I don't care about it. Okay, so we can determine rate law of any reaction if we know the slowest steps, and that's the beauty of the mechanism. So if you break one reaction to, you know, like elementary steps, when I say elementary steps, in like how many steps you have, each one we call it elementary steps until we get to the product. So for example, from here we start with 2NO, we get NO3 and NO. Okay. NO is one of the product, but NO3 is not. We use NO3 here, like we can use NO3, and we can see this one is NO3. NO3 plus CO, we get NO2 plus CO2. Here, 3 carbon, 3 oxygen, 1 oxygen, 4. Okay, so we use the intermediate again. We react it with CO, second reactant, when we transfer it to the product. Okay, so as you see, concentration of CO does not matter, because concentration of, or the CO, we use it when we are dealing with the slowest, fastest step. So it doesn't matter really, like how much we have from it. Yes, if it's like if it's low or limiting reagent, it's gonna, it's gonna limit the amount of product we generate, but it's not gonna determine how fast the reaction is moving fast. Okay, for one cycle at least, for one cycle, concentration of CO does not matter. Okay. And here I have two reactions. First reaction, it says 2NO2 plus F2, we get 2 mole of NO2F. And when I look to the graph, I see energy versus reaction progress. That means when you are moving from reactant to product, what's the change with the energy? So here, reactant, transition state, and then I call this one intermediate. This is intermediate. Okay. I got F. Okay. We don't have F on the reactant or a product. So F is the intermediate that we generated. F, it will be used to generate a product. Okay. And when I looked at the barrier of the second step, is really small. This is the first barrier, and that's going to be the second barrier. The E1 is bigger than E2. So that means the first step is the rate determining. So first step is the rate determining, or first step is slow. So first step is slow or rate determining. In this case, activation energy for first step smaller than activation energy of the second step. So second step, it will be the slow one or the rate determining. So step 2 is slow or rate determining. Okay, so just by looking to the graph, you can guess which one is the rate determining step. First one is bigger, so the first one is going to be rate determining. Second step is bigger, so the second step is going to be rate determining. Okay, and last thing from this chapter is the catalyst discussion. What's a catalyst? Catalyst is the compound that we use it to speed a reaction. For example, like we use nickel catalyst to transfer liquid oil, okay, here, liquid oil to solid oil. The reactant is the oil. This one, product. What's the role of nickel? Nickel is a catalyst. It will speed this reaction. So because it says catalyst, I should get it at the end. So I'm going to say nickel plus oil, which is going to be liquid. I get nickel again plus this time oil, it will be solid. So we used to do this one and use nickel, but because nickel is expensive, we had to come with methods to recover it because it's not cheap. You can't toss nickel easily, and we used to transfer oil, liquid oil to a solid because it was kind of like was better for a matter of keeping oil for longer time. If you have solid oil, you can keep it for longer time and it will not be ruined. But the problem with the solid oil that when you eat it, it will precipitate in your blood vessel and it can give you a heart attack in long term. So we stopped doing this one, and this day, like nowadays, we go with like a liquid oil. Okay, now check the graph. In this case, we have ozone, and ozone, like with if you react with one oxygen, it will give you 2 O2. So 3 oxygen plus 1, 4, we get 2 O2. O2 is just oxygen. It's not gonna hurt. Question is how much O, this is atom, how much O we have in higher level of the like the atmosphere. Not much, because we don't have much. We can say we have we can keep the ozone for longer time. But if you add chloride to it, when you add the chloride, or a chlorine ion, chlorine atom, check this one. It's doing the reaction through 2 steps, but really fast. A barrier is a small one. Any step, if you look the barrier and if you compare it with the activation energy of this one, is way smaller. So you can easily transfer ozone to oxygen and get the chlorine back. Okay, so chlorine is the catalyst. Chlorine managed to speed the reaction, managed to drop the activation energy, and now we got the product. And this is a catalyst. So we must be able to recover it like nickel. And we managed to turn ozone to O2 with a small amount of energy. Okay, this is the side effect of using halide, gases on the atmosphere. We used to use, like this type of gases for, like inside the fridge or other actually gases. And like this day, there is kind of like a huge actually kind of monitoring and how much from these gases we are generating, because if they go to higher level of the atmosphere, they can ruin the ozone, and then if we lose the ozone, then we might get UV light, and that one it can end to cancer. Okay, so a catalyst does not affect either the delta H, okay, Okay, this is not correct, sorry. It's not gonna affect it. This is not correct, sorry about it. Catalyst does not affect delta H of a reaction. Delta H of a reaction. Okay, so the delta H or the gap between reactant and product is not gonna, it's not gonna go up or down, because gap between reactant and product, we call it delta H. In both cases, we did not change it. But the yield, it can go up or down. This is not correct. Sorry about it. I promised myself to fix it before I submit, to print the file, but I forgot to do it. So forgive me, please, about this one. Catalyst can affect the yield. One catalyst, it can speed the reaction, and because it's speeding the reaction in a specific time, yes, it will affect. If you keep the time open, then it might not. Okay, it might not. At the end, you might get almost 100% conversion if you give it enough time. So it's not 100% wrong. It's not 100% wrong if you say, like, if you don't care about the time. If you don't care about the time, yield, it will be the same at the end. Okay, so it's not 100% wrong. But if you say, for example, T after, like say 2 hours, what's the yield? Then that's gonna matter. Okay, then the yield is gonna be different when you have catalyst versus when you don't have catalyst. Okay, so you have to talk about time, and that's the reason, like I said, it's not 100% wrong to say. And like at the beginning, they did not mention time, because they didn't mention time, so it was correct. But if you say after 2 hours or specific time, then this is not 100% correct. Please forgive me about it. Okay, so I'm gonna stop the lecture here, and thank you guys, and have a wonderful time.